Okay, so let's begin the lecture right about now. In this lecture we're going to have a bit more of a look at induction and some examples. So for those who like examples, it's going to be a good day. But first of all, let's recap the theory a bit. We start off with Faraday's law, Lenz law connection. And well, start off by drawing a figure. I have some contour, I call it ds, and a surface enclosed by that contour. And I let the magnetic field flow through it. And now, if I start from Faraday's law, I can show that if I change the total flux in this area, I will create an electric field around ds. So let's look at the connection there. So let's see. I start off by looking at Faraday's law. There you go. And now, to get some idea what's going on here, I integrate over the total surface. On both sides of Faraday's law. The physical meaning of this term is clear. It's the flux of the magnetic field through this surface S. But the meaning of this term is not entirely clear, so I'll use Stokes' theorem to rearrange it. Let's see. And that gives me the line integral of the electric field around the contour. Let's see. So it changes from a surface integral to a contour integral. And there's some minus. Let's see. Okay, a bit tired. Minus dt so there's the time derivative of the flux here and the electric field integrated around the loop on the other side. And now I'll call this the electromotive force. So if I put a wire around here, there's going to be charges that can move due to this electrical field. And then this is essentially the voltage that makes it move. So I'll call this big epsilon. And now we've shown that it's equal to the time derivative of the total magnetic flux through the surface S. Okay, in general we remember that big epsilon, the electromotive force, is in general defined like this. So on a charged particle with a charge q, I take the F divided by the charge and integrate it around some sort of loop. And then the electromotive force is well, in some sense the sum of forces around there on a charged particle. This is the general definition, but in our case the electromotive force is the magnetic one, or the electric one which stems from the magnetic. As we discussed last time, if you have a time-dependent magnetic field, you actually create an electric field, and vice versa. Okay, so in rough terms, epsilon is anything that will make your charges move. So there could be a mechanical source or a chemical source in general. And this is the working principle in electric motors and generators. Everything that converts movement into electrical energy and vice versa. Okay, now I'm going to go through the 3 experiments done by Faraday, which was sort of the, that's where this law came from. He did experiments, and then later on someone realized that this was the law that, let's say, decided what happened in those experiments. So I'm just going to wipe the board, and then we're going to look at those 3 experiments. So, first experiment was the following. Faraday had a lot of permanent magnets stored in his house, so he built himself a region where he had a magnetic field. Some region in space where there's a magnetic field. He took a wire and made a loop with a resistor here. And then he did the following. He took his hand and pulled with some velocity out of the magnetic field. And then by various means he could measure that there was a current flowing here. Okay, that's interesting. If I take the loop and then try to tear it out of the magnetic field, I change the flux within. Well, then there's a current running. Now what if I do the other thing? I leave the loop lying still, I clamp it somehow, and then I pull the magnet. That was his second experiment. And the same thing happened. If he pulls the magnet or pulls the coil of wire, the loop of wire, well, you have the same thing. There's a current running through the loop, causing heating in the resistor. And the final third experiment was the following. He built himself an electromagnet. And an electromagnet will have a time-varying flux density. If you generate a time-variant current through the electromagnet. So let's say you make a coil, many loops, so wire. You run a current through it. When you ramp down the current, then you change the magnetic field, right? And there you go, you have the same result. You had a current flowing through the loop, same as in the other 2 cases. So it seems that it's not, well, you have the same result here, which can be summarized in the law we know so well now, that the electromotive force is equal to minus d phi dt, where phi is the total flux in the loop area. And especially the first 2 ones were important for Albert Einstein when he studied the theory of relativity. Because it seems now that, I mean, seems logical to you guys, because you know, you've always been told that the laws of physics are the same in every frame of reference. This was not obvious to Maxwell. Maxwell believed in some sense, God-given or fundamental frame of reference, which could be said to be standing still inside that frame of reference. And that was called the ether. Now if you imagine that the ether was standing still with respect to the magnetic field here, and with respect to the loop here, then you might expect to see different results. But you don't. And this was sort of a puzzle to, well, at least to Einstein thought this was funny. So he sat down and he had to think a bit, I guess. But after a while, he figured out the special theory of relativity. And I think one of the most important postulates there is that in any inertial frame of reference, the laws of physics are the same. And then, of course, it follows sort of trivially that these two experiments would have to yield the same result. Because if one thing is moving or the other, well, that's just a change of coordinate system, which shouldn't change the laws of physics. Right here, it's not so obvious that this is the case, of course, because it's a completely different process that changes the flux and gives rise to the current. Okay. And yesterday we gave an example application of this, which was the eddy current brake. And now I thought we could pass around this magnet, and this disc is aluminum, so it's not magnetic. But if I do like this, I feel no force. But if I rub it against, I can feel that the aluminum is trying to slow down the magnet because of the eddy currents. And you can demonstrate this by holding it up and sliding it down. You see it goes really slowly, even if it's almost vertical. Now before I pass it around, I want to give a few words of warning, because this is a pretty strong magnet. If I put it down on the table and push it around, you can see it jumps to the screws in the table. That's quite strong. I know a girl who bought this, a healing magnetic bracelet, mumbo jumbo stuff. But anyway, she put it on her hand, and then she went to write something on her laptop. And then as she puts her hand down, the laptop just dies. So it might be good for you, but it's certainly not good for laptops or mobile phones or anything like that. So keep it away from metals, because if you drop it on metal, it actually might. This is a quite brittle material, so it might shatter and you might get splinters in your eye. I mean, it's definitely worst case, but don't test your chances. So don't put it near metals or magnets or keys, and don't put it near anything electronic, because that might be expensive. So with that warning in mind, try to slide it, try to rub it, or vice versa. You could try to pull the aluminum without touching it. Okay, so I'll pass it around so you can feel the eddy current brakes on your own. Just be careful. Okay, yeah. So as we discussed last time, the advantage is you don't have to use friction to slow the magnet down. You just have eddy currents flowing in the conductor. So there's no mechanical wear and tear because of the brakes, which is very nice if you have something that's moving really fast, like trains. Okay, while some of the guys are playing with magnets, I'll give an example of a different application, which is crack detection. I'm not talking about a drug now, if you're wondering. I'm talking about cracks in metal. So if I have some sort of metal surface, let's say iron. Now I put a coil up here. And I make an alternating current source. So you have some magnetic field generated from this, but it's varying in time. So I'm going to induce eddy currents on the surface when I hold the coil down to the surface. But if I'm approaching such a crack, well, first of all, this causes some heating. But now if I'm approaching a crack, there's not so much metal to conduct. So the current is going to start running circles around the loop. No, sorry, around the crack. And hence I'm going to get some local heating, which is stronger than over here. So in addition to this coil stuff, which sort of generates surface heating, I put an IR camera pointed towards the crack, or the place I think there might be a crack. And if I see some local heating from the infrared camera, well, then there's a crack at that spot. This was developed by Elkem. And it's known as something like the thermomatic. So was that explanation clear? Any questions? Nothing? Okay, that was pretty much that. The next example is a bit more involved, and that's the infamous railgun. You might have heard of railguns in computer games or some such, but you can actually build them. And the next example is to show you the theory behind how they would work, how they do work. Now the railguns are mostly used in science fiction today, but there is actually research going on, and I actually heard people say that they put them, Daniel actually told me that they put them on ships these days, and I know that the US Navy is doing research on it. I know that because it says so on Wikipedia. But I'm guessing that's true. It says there that you can actually accelerate a 3-kilogram projectile up to 7 times the speed of sound. And that's quite a bit. I mean, to get something that's 3 kilograms and in a few meters or not too long, sort of get it up to 7 times the speed of sound. Well, usually you can't even begin to approach that speed by jet engines. You need rocket engines. So it's a fuel-less rocket, more or less. And practical applications might be, of course, military. But also you could do research on a lot of subjects doing this. So maybe I'll write it down. So there's military. There's also, you could do research on, let's say, aerodynamics. If you want to get up to Mach 7 without building your own rocket, it might be convenient to use a railgun. Also, if you want to see what happens to materials when they crash together, like doing research on impacts, then this is an interesting alternative to building rocket sleds or whatever expensive equipment. It's been discussed, at least in science fiction, to use this as a satellite launcher or a partial satellite launcher. It's very expensive to bring a lot of fuel along, because then you have to accelerate not only the payload of the rocket, but also the fuel. So if you can just accelerate the rocket without all the fuel, you could use a lot less energy. Okay. And also, in fact, some people are doing research on using this in fusion reactors. That's something called inertial fusion. You've all seen, I hope you've all seen the tokamak design of a fusion reactor. If not, it's basically a donut. And they do some tricks with magnetic fields around here. And they put a plasma inside, and they run currents through the plasma and so on to make it stable. It's a big mess of magnetic fields and electric fields and plasma physics and I don't know what. I don't know half of it. Anyway, it's a big and complicated machine to build. So some bright heads thought that, well, what if you just smashed things together? I mean, then the density would be high, at least for a while, and you could hope to get some fusion. And I'm not sure if railguns can deliver that, but people are trying to do research on it anyway. Okay, so first of all, I'm going to make a principle sketch for how a railgun works. First of all, you need a voltage source, of course, a big one. You run a current through a wire. Or a rail. There you go. And now I put a projectile here. It doesn't have to be a bar, but I'm going to make a simplified model so that we can actually do some calculations of this on the blackboard. And the current is flowing through the projectile itself, so it has to be conducting, or it has to be sitting inside something that is conducting. So the current is running through, and well, as we all know from the Biot-Savart law and the right-hand rule, we get a magnetic field that's, let's see, it should be into the board. And similarly, in this direction, there you go. And now as the projectile starts moving with some velocity, well, then there's a change in flux. Because as I expand the area, there's more and more flux lines being generated here, so to speak. So let's see, to get some dimensions, I call this D, the width between the wires. And X is the distance from the, well, from somewhere over here to the projectile. Anyway, it's the position of the projectile in some coordinate system. It shouldn't really matter too much. And now we're going to try to estimate what kind of acceleration can we do if we use the stuff we find at home. Let's say you find a couple of long tubes of iron, and then you pull as much current as you can from the wall socket. How high can you get to get some basic idea of the order of magnitude of stuff here. So we're going to use some approximations to be able to do the calculation. And that's that there's no resistance in the wire. So I make a big fat rail, and I squeeze the projectile down so there's good electrical contact between the rail and the projectile. Of course, this might not be the case, but let's try that for now. We're going to keep the rails cylindrical. So it's shaped like a long cylinder. And the distance here is going to be much smaller than x, because then I can approximate the magnetic field as only coming from this and this wire. It shouldn't be too much of an approximation, I believe, if you make a big, long railgun. And finally, I'm going to say that I is constant. And I'm pretty sure it's going to be really hard to keep the current constant as the projectile starts flowing, but well, let's try and see what happens in that case. I think I'll keep the sketch for now. Okay, now first of all we have to ask ourselves, what is the electromotive force? Well, it's of course equal to the flux, the time derivative of the flux. And I'll write down a simple expression for that, and that is, well, it's x, now let's see, d dt of the flux, and the flux is x times d times the average magnetic field. So of course, there is no variation as I go along the wire, because I just regard them as infinitely long wires as an approximation. But there is variation here, of course, because the magnetic field is stronger, closer to the wire. And for that reason, I have to calculate the average across, but in this direction, it's going to be more or less invariance, as long as I keep the railgun long. So, well, the B average is going to be constant, because it is an average, and the D is going to be constant. So the thing that's going to vary here is the X. So this simplifies somewhat to minus D, B average, dx, dt. Okay. Now, first of all, what's B average? And that I can do, of course, by integrating the whole area and dividing by the area. So I calculate the flux and then divide by the area. But along the x direction, it's just going to be a multiplication by the length and then division by it again. So I don't have to do that. I'll just do like this. Okay. To set up the limits of the integral, let's see. This is a finite width rail. I give it some radius r. Let's see, this is 2r. Okay, so I have to integrate from, not from the center of the wire, but from the radius of the wire. And not up to d, but d minus the radius of the wire. Let's see, d minus r. Now the magnetic field is equal to the sum of the contribution from the two wires from the principle of superposition. And let's see, that's basically the following. There's a prefactor. There's some constants, the current. And now let's see, I mean in a coordinate system, this is x. So this is the set direction. Let's see, set hat. Okay, just to define the coordinate system. And then, yeah, so this integral goes from here to here in the set, along the z axis. And the magnetic field from the lower one is proportional to 1 over z. And from the upper one is 1 over z minus d. You remember that the magnetic field from an infinitely long wire is proportional to 1 over the distance, and this is the proportionality factor. Okay, and I think I'll just do the integral. And B average is u naught I over 2 pi d. There's a factor 2 here, because there's two terms which are sort of symmetrical. If I, instead of integrating from here to here, I integrate from here to here. Well, that would be the same as switching the terms, so it's basically a factor of 2 times the contribution from this one. And 1 over z, that gives a logarithm. And those are the upper and lower bounds, as you can see. Now I'll approximate a bit more. Well, it's not. I have to make some sort of assumption about what is r and what is d. Because if, well, d has to be bigger than r, of course. But it also has to be quite a bit bigger, because I have to fit the projectile in there. So let's say that d is equal to 10r. Well, then this is essentially 10 minus 1 divided by 1, so it's ln of 9. And e is almost, I mean e, the exponential e, it's 2.7, etc. So this is going to be more or less 2. And because it's a logarithm, it doesn't change all that fast. If I change the geometric factor a bit, it doesn't completely change the calculation. So if I just set it to 2, I should be sort of okay. So I can further I can just then take away these factors of 2, because there's one above and one below the fraction. Okay, right. That's that. So now we have the flux. I take up this now. Okay, so I'm going to look at the power balance in this circuit. The P, well, it has two terms. The first is the ohmic loss, the resistance times the current square. And then there's the electromotive force from the movement of this projectile. And that's big epsilon times I. And now I'm going to neglect this term. I'm going to just say that I got a big, nice rail that conducts really well. Maybe a superconductor, who knows? And I'm just going to look at this term to see how good can it get in principle. Okay. And then I can write this down in the following way. The power developed is, of course, the force times the velocity. The force on an object times the velocity of the object. That's basically Newtonian mechanics, so you all know that from before. And that's equal to epsilon I. Let's see, and I write that down as I. That's this I. And then it's d times mu naught I over pi d dx dt. Let's see. There's 1 over I in the B average here, but there's a d here. So these will cancel. And there was a factor 2 here, but there was also a factor 2 from the logarithm. So those cancel. And that's pretty much it. I can take out this term, this factor, because it's the same on both sides. And the force is what's left. It's mu naught over pi times the square of the current. So you can see this is really nice. If I double the current, I get 4 times the force. That's a nice property. So you get a big fat current flowing and you got a lot of force. And this you can, well, if you then again neglect friction, which is ridiculous, but we'll do that because it's on the blackboard and we don't have too much time. I'll just set this equal to the acceleration of the projectile. M is, of course, just the mass of the projectile. Let's see. Now, let's say that this is more or less the final theoretical result. So, let's see, I go home and I get a transformer to get a low voltage. I get nice conductive rails that have little resistance. So let's say I could get out of a big wall socket, I could get 100 amperes. I think you could do that if you have a low enough resistance in the wires. And let's say a mass of 1 gram. That's sort of macroscopic. It could be 10 grams, and then, of course, the acceleration will be 1/10. So we'll get some idea of what's going on here. Now, if I set A is equal to the force divided by the mass, I get the following. Let's see, mu naught over pi m and I square. Okay, and mu naught is 4 pi times 10 to 7. There's a pi here, so there's not going to be any pi in the result, sorry. So it's 4 times 10 to minus 7. And I am just going to put in SI units all the time, and the answer should be fine. So the mass is 10 to minus 3 kilograms. So it's 10 to 3 when I get it, put it on top again. And then there's 10 to the power of 2 square, so that's 4. So a rough estimate says 4 meter per second square. If I did this correctly, it should be 4, 7, yeah, okay. So by well, I think this is something you could almost do in your home. It would be hard to get rid of the resistance, the friction and so on, but the acceleration is quite noticeable. It's half of the acceleration of gravity, more or less. So the electricity bill might be big, but you might have some fun. I'm not saying you should go home and do this, by the way. I don't accept any responsibility for experiments. I'm doing theory here, not experiments. So any questions on railguns? Nothing?
I'm not sure about how you take the effect. You cancel the R minus square.
I just say that the resistance is small.
Okay.
It's an approximation. I think if you want to do this for real, if you want to build one that gets you to Mach 7, I think you're not going to neglect this term. Yeah. I just wanted to see how good could it get in principle if I got rid of all the sort of opposing terms, right?
Yeah, because the electromagnetic force has a minus sign, so they are working against each other. Yeah.
Well, I didn't do any calculations on the signs carefully, but I'm pretty sure that if you get something moving and you get a current flowing, they're not going to cancel each other out. You have to supply the energy. So from a physical argument, I would say that you have to add them. Yeah, but you might be right. There's a sign error somewhere. But from physical arguments, I see that this is how it has to be. Yeah. Yep. And also, you might notice that in the epsilon there is an I as well. So this is actually also an I square term, right? Here in B average, there's an I. So this is also an I square term. So it's not that as I increase the current, this term grows much more than this one. Any other questions? Nothing? Okay. As a small homework, I would suggest, just if you're interested, that you could look up coil guns. And the coil gun was originally suggested by Christian Birkeland. He's a famous Norwegian physicist, and I believe he was nominated for the Nobel Prize in Physics 7 times in a row or something like that. If I remember correctly. I don't really know why he didn't get it. But anyway, he patented the coil gun, and that's basically this. If I have some small piece of ferromagnet, let's say a nail. So let's say iron. That's a nice example of ferromagnet. And I put a coil here. And let's say maybe a tube to let the ferromagnet slide through. If I ramp up the current here quickly, then this guy is going to feel a force. It's because of the magnetic properties of the material, it's going to get magnetized and it's going to be attracted by the other magnet. And then as this projectile proceeds to over here, let's say, I shut down the current as fast as I can. And this is actually one of the physical limitations of a coil gun, is that you can't shut down the current as fast as, you can't just turn it off. That's the whole principle behind a coil in a car, right? And then, yeah, so while it's here, I is large. And when the project is here, I try to make the current as small as possible, because otherwise when the projectile gets through, it's going to slow down again. So I cut off the current, and then it's going to fly out here with hopefully a large velocity, or as large as you would like. And this is actually so simple that you could make a nail gun out of it. You just get a power cord, and you get some sort of switching mechanism. You let the ferromagnet be a nail, like the ones you put in your walls at home, if you have a wooden house. And then, well, you don't need a compressor or any of that big, expensive, heavy equipment. You just need a power plug. Okay, so I'll leave it for you as a homework to try to understand how that works, but only if you're interested. Okay, so well, it's 5 minutes left, so I think we'll yeah. I'll continue after the break.